In this chapter, we're going to discuss about bipolar junction transistor, also called as BJT. So to cover the topic, we'll go through 4 sections. The first sections we will go through a brief introduction about the transistor, and then in second section, in order to be able to start to work on transistor, we'll explain what happens behind it. It means how is a transistor made, what is it made of, its construction, the structure behind it, and therefore we'll also look into the characteristics of a transistor that we need to take into account to be able to use it. And in the third section, we will study several transistor configuration in a circuit, and at the end we will try to look at certain application that we can do using a transistor that is of course configured in a certain configuration that we've seen in the previous section. So we begin with an introduction. So the first, who have found the first transistor? The first transistor have been studied for quite a long time by a man named William Shockley, who was working with Bell Laboratories. And finally, at 1947, with the help of several colleagues, he has basically demonstrated the operating of the first transistor. And just like in diode, if we look at this component that are made of semiconductors, they are usually found at the same time, and they were found basically to make components that will work for telecommunication industries, telecommunication technologies, right? So just like a diodes, it also uses the properties of PN junction to operate, right? It uses the properties of PN junction just like in diode. So in previous chapter of diode, we have basically explained quite briefly on how do we create a P and N junction on the semiconductor materials, right? And now it also uses the same properties of that P-N junction to make a transistor works, right? So here we have a figure, of course, in the middle is William Shockley with in his labs demonstrating the first transistor that they have found in 1947. On the left side of the figure, what we have here is basically is the first transistor that they have demonstrated. So the size as shown in the figure, it is quite a consequence in terms of the dimension, but now we know that the PN junction basically use the properties of having extra electron or having extra holes in those regions. It means that it only needs a few atoms. Even if we only have a few atoms, a PN junction can work properly. So today what happened is basically that's the prediction of the Moore's law. PN junction can basically work with only a few atoms. It doesn't need a very long size, a very huge dimension of a PN junction, P material and N region, P region and N region. So basically today's size of a transistor has been reduced until the size of a few nanometer, right? A few nanometer. So basically here we can see on the right hand side is the type, typically type of transistor that we can find today. So the size is basically 0.4 millimeters times by 0.5 millimeters, which is 40 by 50 micrometers. But of course a smaller can be found. Basically that's what we can find in circuit chips, right? Like your microprocessor or any other integrated circuits. They are very small at the size of a few nanometer. So in our circuit chips, for example, in a microprocessor, in a processor like the one that you find in your PC, what make a circuit chip is made of basic modules, which are themselves made of logic gates, and these logic gates are constructed by a combination of a few transistors. So basically, a transistors is the main component that makes a logic circuit or logic gates work, right? So that what makes our chip, our integrated circuit or our microprocessors. And in these chips, basically the size of these transistors are very small. So this is a depiction of basically a view under a microscope of a single transistor at a very small size of a few nanometer. So in general, how does it function? A transistor basically function as a switch and as amplifier, but basically in logic gates, its most important function is as a switch. So it's the component that let currents go through it or not let current goes through it, which also defines the state of on or off of a switch, which means it is the component that defines the state of, usually on we can call on as state 1, off as state 0. So it's the component that create the binary state in our logic circuit. So it is very important to know how a transistor works, and it is without transistors all applications that needs computers and computational method will not be available today. So now, in order to be able to understand how does a transistor works, let's go inside the transistor to look at the transistor structure. As mentioned before, it uses a p-n region just like in diode. And just for a reminder, for revision, what are n types and p types region? N types region are the regions that contains free electrons, which we call negative carriers, or p-type regions, and the other one is p-type regions which contains free holes, which also called positive carriers. So basically they are semiconductor materials like silicons or germanium. For p-type, it was doped with impurity that create holes, for example by boron. As for n-types, is basically the semiconductor is doped with material with an extra valence electron that creates a free electron, right? So this is n-type, which is also called negative carrier. This is p-type, which we call positive carriers that have holes, and n-type that have extra electron. So how does this work for transistor? Well, a transistor, instead of having just two regions, P and N, just like in the diode, we will have three regions. Instead, we will have three regions. And in function of how do we arrange those P and N regions, we'll have two types of transistors. One is what we call NPN transistor, and the other one is PNP transistor. Well, it speaks for itself. Basically, NPN means you have two N region and one P region in between, whereas for P and P you have one N region in between, which have around it two P regions, right? So the transistors regions, basically by doing so, you have these two configuration of P-N region. Is either PNP or NPN, right? And the terminals are called with a specific name, with a given name. So the names of the terminals are, one is what we call as emitter, the one in the middle is what we call a base terminal, and the other one terminal is what we call collector terminal. For example, here in example of a PNP transistor, we have the N as a base, and both P serve as collector and emitter. So here is the circuit symbols, but before we go into the circuit symbols, we will explain in the next slides why do we have this kind of circuit symbol and what does it mean, these arrows. But before that, for example, now if we look into NPN transistor, as it's the opposite of what we have in PNP. In the middle we have base, which is a P region, and around it we have the collector and emitter that are made of N region, right? So what is emitter? Emitter, we start with base because this is the one that is in the middle. Base act as control region. It is the region that allows carrier to flow across the transistors, right? Whereas for emitter and collector, it depends on, basically if we look further, there's P there's P plus, there's N plus. So the P plus or N plus is what we call emitter. So it's the component that send the carriers, whereas collectors is basically it's the region that collect the carriers, right? So we'll go into more details in the next slide. Here, in order to explain what happens in the emitter, in the base, in the collector of a transistor, we'll take an example of a specific one, which is basically the transistor that we use the most, the example of an NPN transistor, right? So in NPN transistor, what we have is basically we have two N region, and in the middle we have in between the N region a P region, right? So the N plus, what does it mean by N plus? N plus means basically we have a region that is strongly doped by the impurities. So the doping is slightly stronger. It means we have more negative carrier on this N plus region. Whereas for the other N region, it is moderately doped, right? So this moderately doped region is just called N. It is the collector. So emitter is the slightly more doped, whereas the collector is the region that is moderately doped by the impurities. And of course in the middle we have the P region, and this one we are not confused anymore because there's only one P region in the middle that serves of course as base. So let's see what happens in this transistor. Why do we have emitter called as the one that send carriers, whereas collector as the one that collect carriers? Okay, let's see what happens if we connect the NPN junction, the NPN region, with a power supply in this direction. So what happens once we have the power supply in this direction, automatically we will create barriers inside the junction, right? We will create barriers inside the junction. So barriers inside the junction is of course due to either the region being forward bias or reverse bias in regard to the power supply. For example, if we look at the first part of PN region, we have the power supply, the positive side that comes to the negative side. So this PN region is basically in reverse. It is in the reverse bias, whereas for the other side, on the other side, this PN or NP region, now on the other side we are basically in forward bias. Why? Because the N region is in contact with the negative side of the negative terminal of the power supply, right? So the next interesting things that we need to look at is basically, let's look at the voltage across the regions, right? So for example, now as we connect it to a power supply, there are three voltages that we can measure. The first one is VCE, so it's the voltage between the point collector and emitter. There are two other voltages, so it's the voltages at the depletion region between B and E, we call it as VBE, and another voltage across the depletion region between the base and collector, so we call this one as VCB. If you look into if we write a KVL, a Kirchhoff voltage law, using these three voltage, we will remark that VCE is equals to VCB plus VBE. So let's see VCE. So VCE, if I can draw using a pen here, let's see VCE to show the direction, to point the direction of the voltage. So VCE is the voltage from E to C, right? So VCE is in this direction. VCE in relation to VCB, so VCB is from B to C, so this is VCB, and VBE is from E to B, so this is VBE. So if we look into at this KVL, it can also be observed basically on the circuit symbols. So where is VCE? VCE is this voltage. Now let's just write the parallel of the things, but on the circuit symbols. And then next thing is VCB. So where is VCB? VCB is basically this voltage. It's between the point B and point C. And the last one we have VBE. So VBE basically is this voltage between the points E and B, right? VBE. So if we look into these vectors, VCE is basically the addition of VBE and VCB, right? And there's one thing that we know here is VBE, right? It's VBE. VBE is basically the depletion region between the N and P region over here. This is the same thing as what we have observed in diode, right? This is the same thing as what we have observed in diode. And if so, here we have therefore VCE equals to VCB plus 0.7. This is of course if we consider that the semiconductor material that we have here is silicon, right? As for VCB, we don't know what the value is because it will be influenced by something else as well. But VCB is basically the voltage across the point C and point B, right? So this is the equation that we have right now. So what will happen next? What will happen next? The next thing that we will do is that now at this condition, nothing will happen, right? Because we have VBE, which is the forward bias voltage of 0.7. The current will not be able to flow, right? Because now the current is in this direction, and in this direction we say that the PN region is in reverse bias, so it will not be able to flow. It will not be able to flow, so no currents flowing at the moment. So the next thing that we want to look at that would be very interesting to do is if we put a voltage at the base right here. So the thing that we're doing right here. So what we're doing right here is basically we try to get across the bias voltage of 0.7. If we get across the bias voltage of 0.7, it means we can cross this depletion layer. When the voltage is applied to the base at a value of at least or larger than 0.7, what happened now, we can go across the depletion layer. And who want to go across the depletion layer? The thing that want to cross the depletion layer is basically the extra electrons that we have in emitter. Emitter means we have N plus, it's highly doped, so these electrons want to go to the other side. So now we have current flowing. We have current flowing in the transistor. So that's why we call now the base. We call the base, and the base basically acts as a control region. If there is no IB current in the base, if you don't supply any current in the base, then the transistor won't be operating. So there will be no current circulating. If there's a voltage that exceeds 0.7 applied across VBE, then a current will be able to circulate from collector region to emitters region, right? From collectors region to emitters region. So that's why we call that's why we call emitter as the portion that sends the carrier, so it sends the carrier across, and the collector as the region that collects the extra carrier. But again, the current basically it circulates in the direction of the power supply. So these arrows, so if we look at the symbols, again here we look at the symbols. So these arrows from B to E, from C, so basically CB to E, this represent the direction of the current that's flowing across the transistor. And of course it only flows if we apply a voltage across VBE. If we have VBE, then we will have, currents circulates across C and E. So this is the The same thing that we have explained in previous slide also happens to the other type of transistor as well. So be it PNP or NPN, the same processes occurs in both type of transistors. Therefore, we can deduce the direction of current across the junctions of the BJT, right? As we've seen earlier, in terms of voltage, we have deduced that there is one equation of voltage that we have found. This equation of voltage is very important, and it is one of the equation that we are going to be using when we calculating different circuit analysis where we have transistors. So again, I repeat, VCE, the voltage across the collector and the emitter, will be equals to VCB. So VCB is the voltage between the collector and the base, right? VCB plus VBE. And again, we know that VBE is the bias voltage of a PN junction. So it will be depending on the material of semiconductor. For a silicon, it will be 0.7 volts. For germanium, it will be 0.3 volts. The other equation that we would like to look at is the equation of current. So as we explained in the previous slide, the flow of current as the junction B, as the region B is supplied with a voltage that is superior than the bias voltage, what will happen in, for example, in a PNP junction, the current will flows from the emitter, and then it will get into the junction. So a small portion will be used in the base, and another bigger portion will goes into the collector. And for the NPN transistor, the currents come from the collector, right? Comes from the collector, and a small amount also comes from the base, and the sum of them will goes out at the emitter. So we can write basically the equation of the current. For example, here we would have, if we consider this junction at the base as the node of separation of the current, then we can apply KCL. For example, the sum of entering current equals to the sum of leaving current. So we will have here IE equals to IB plus IC. So that's where we got the equation of current across the junction of a transistor. So again, it's the equation of current across the junction of a transistor. Is IE equals to IB plus IC. If you look here, it's the same thing. Is the current flows in the opposite direction in an NPN transistor. Again, the sum of entering current, which is IC plus IB, equals to the leaving current, which is IE. So again, IB plus IC equals to IE. Right. So in the symbols, the arrow shows indicate the direction of flows. So that's how PNP and NPN functions due to the properties of the region P and P, right? So in previous slide, we've seen two relations between the voltages in a transistor and between the currents across the node in the middle of the transistors at the base, right? So this is the relation between the voltage, and this is the relation between the currents. And from the properties of the transistors, where most of current will be circulating from across E and C, and only a small current that will circulate into the base, IB. So emerge another properties which is also very interesting, is that as we supply a very small amount of current just to overcome the voltage 0.7 volts, a very huge amount of current can be circulated across the transistor just by applying a small command of IB. A big amount of IE and IC can circulate across the transistor. So this relationship between the two parameters of IC and IE, IC and IE, is the parameter that we call the gain of a transistor, right? The gain of a transistor. Basically, IB is very small, right? IB is very small, but it can produce a very large IC and a very large IE. So that's why we call a transistor doesn't only act as a switch, it also can act as an amplifier. Just by applying a very small amount of current, it can allow a circulation of a huge amount of current. So what is the relation between this IB with IE and IC? What is the relation between IB with IE and IC? So the relation depends basically on the configuration of the transistors mounting. So here we have two configuration of transistor. The first one is what we call common emitter, and in the configuration of common emitter we will have a common emitter current gain, which we call beta. What is current gain? The current gain is basically the ratio between two currents. In a common emitter is the ratio between IC over IB. So the ratio between IC over IB. So we'll get a huge amount of IC with a small amount of IB, and the ratio between IC and IB is what we call beta. So this is for a common emitter current gain. What is common emitter? What is common emitter configuration? Well, the explanation that we use here to explain the operation of a transistor is basically what we call common emitter configuration. Common emitter means, so in the next slide we will see the types of configuration, but this is basically, common emitter is basically the most used form of transistor configuration. So what is common emitter means? Common emitter, simply put here, common emitter is when we have the negative terminal or the ground of the base and the ground of the the emitter, are joined together. So we have the base and the E are joined together. So here basically what we have here is, if I have to draw it over the symbols of the transistors, basically we have this point and this point joined together at the ground, right? And you might ask, what about the collector? Isn't collector is also connected to the base? Well, no, collector is not directly connected to the base. There is a power supply between the collector and the base. So between the collector and the base, basically that we have a power supply. So if I have to draw it over here, basically what we have is, between the collector and the base, we have a voltage supply. So voltage supply like this. So when the base and the emitter is directly connected, that's what we call common emitter. In common emitter, we will have beta as the gain, so the gain between IC and IB, right? So this is another very interesting and very important characteristic of a transistor. So let's quickly look in the next slides the other type of configuration, because the other configuration here, for a common base configuration, we will have a current gain which is now called alpha. It is now the portion of IC over IE. So let's look at the configuration quickly. So here we have the three type of transistor configuration. So transistor configuration define the connection of the transistor with its input and output voltages, right? So the three types are common collector, common base, and common emitter. So let's start first with common emitter, because common emitter is basically the form that we use the most. So in the middle we have the common emitter. Common emitter, as we said just now, is when we have the base and the emitter connected. So base and emitter is connected, where we have the small voltages that supply the current IB. So now we have P and P here, right? So IB is coming out of the N. If we have the supply of the small voltage to overcome the bias voltage put in between base and emitter, so we call it as input. right? So the bias voltage to switch on the transistor is what we call the input. So if we have it between B and E, that's what we call common emitter, right? And we measure the output at VCE or VEC. I prefer to say VCE. So VCE is in this direction from E to C. If we measure the input between B and E and output between C and E, is what we call common emitter. And if you remember in previous slide, if we are in common emitter, then we have a gain, a current gain of what we call beta with the symbol beta. The current gain is therefore the ratio of IC over IB. IB is very small, IC is larger. For the other type of configuration, the other configuration that we might use is what we call as common base. So common base is the one that we have here. Common base is when the bias voltage to switch on the transistor is put between the base and the emitter. So we put the input between the base and emitter, and the output is measured between the base and the collector, right? So this is the second type of configuration that sometimes we use as well. And in this case, we have the you can refer to the previous slide. We have the gain, which is now called as alpha, equals to IE over IB. Right? It's IE over IB. And the last one is what we call the configuration in common collector. Well, it's basically very rarely used, and we're not going to look into it in this particular course, right? So just now we have seen all the configuration that we can be using. We can use when we use a transistor. But starting from now, what we're going to concentrate at is we're going to concentrate only at common emitter configuration. So for this common emitter configuration, what we're going to look at now is the characteristic of current voltage characteristic in a common emitter configuration. So the first characteristic is what we call the input characteristic. So what is the input characteristic? Input characteristic basically describes the value of current at the base, IB, as a function of versus VBE. So VBE, where is VBE? VBE is where we put input, our input voltage to excite the base of our junction, our transistor junction, right? So for example, here is an NPN junction. So to excite that P junction in the middle, what we need to do is we need to put a VBE and input voltage, right? So this first characteristic explains how much current can we get from a different value of VBE. So this one is a very simple characteristic. This input characteristic is just like a characteristic. If you have, I think by now you have figured it out, it's the same characteristic as a characteristic of a diode. So in order to have current circulating in the transistors, to have IB, what we need to do is we have to go beyond the bias voltage of the junction. So the bias voltage of the junction is of course between 0.6 and 0.7. For silicon, we would say it's equal to 0.7. So before 0.7, there will be no current injected into the base. So basically, as consequence, the transistor will not operate. But as we increase the value of voltage VBE, the input voltage, as it goes beyond the value of the bias voltage of the junction at the base, then we will start to observe that a certain amount of current will circulate across the into the base. So the amount of current that circulates also depend basically on the amount of the VCE. It is also influenced by the power supply that we put in VCE or across VCE, but the variation is very minimum. So here it shows, for example, if you put 1 volt, 10 volt or 20 volt on VCE, the current will have slight variation like this as we increase VBE. right? So here it explains everything that I've said verbally. So the final conclusion that we need to take into account, that you have to remember, is only one thing. What is it? It is to remember that the transistors will only be turned on, will only operate when you have VBE equals to or larger than 0.7 volts. Now, after we have seen the input characteristic of transistor operating in common emitter CE, I will call now by now CE configuration. Now we look at the output characteristic of the CE configuration. So what is the output characteristic? As we have seen in CE, the input is VBE, but the output is now VCE. So let me draw a bit the voltages so that we remember where it is. So just now the previous characteristic is on VBE, so this is the input. Now what we're looking at is basically it's the output. So the output is here for a CE configuration. So the output is VCE. So the output characteristic that we're looking right now, so we'll go directly into the graph. The characteristic that we're looking right now is the current IC. Let me get my pointer. So as we're looking at VCE, the voltage output, and also the current IC, because the current IC is the consequence after having VCE. If it allows circulation of current, then it will be current IC. So we're looking at a graph of IC, the current in the collector, across the collector, versus VCE, right? IC versus VCE. The characteristic depends on also depends on the current at the base, right? The current at the base, it's only because we know that VCE and VCE is there, but IC can only be observed when we have IB. So in function of IB, as IB varies, IC will also varies. So this variation is represented by different curves. So these different curves, all different curves represent the value of IB. So this first blue curve is the curve when we have IB equals to 0 amps, and as we increase, what basically we're doing is that we increase the value of IB. So as we increase the value of IB, what's the relation between VCE and IC? So there are basically three regions. The first region is this region here. So we'll start with this region. This region is what we call the cut-off region. Cut-off region means basically is the region when we will not observe current, we will not observe IC, or a very small IC. We will observe very small amount of IC. When we will observe cut-off region, basically the cut-off region is when we will have an input condition of 0. So if we have IB equals to 0, then we will not observe any IC, because again, remember, if you remember the relationship between IB and IC, the relation is basically the gain of amplification, beta, right? If you remember, if I can write just to remind. So the relation between IB and IC is basically beta. Beta is IC over IB, and it can be reflected here as we see that, for example, if we look at the value of IB, they are very, very small, in the order of microamperes, but at IC we have in the order of milliamperes. So here we have the gain at the order of 10 to the power 3, right? 10 to the power 3. So the first region is what we call this cut-off region. Cut-off region basically is when our current is 0 ampere. We will not observe, or we will observe very small amount of IC. And then the next region, we'll look at the limited region first. So the first one is cut-off region. We've seen this one. The next region is the next limiting region that we will not use. So cut-off region is the region that we will not use. The next region where the transistors will not be very useful is the region that we call the saturation region. So what is the saturation region? The saturation region is when we have a very small amount of VCE. Our VCE is too small. So what happens when our VCE is too small? We will have an IC that is basically the amount of IC is situated in this region, right? The thing that we want to the transistor to operate is basically in this region, in this active region. In this active region is the region where we have the curve. We could consider the curve as linear here, and the linearity represent basically the gain, somehow represent the gain B, the gain beta. So we have the relation between VCE and IC linear. So the relation are linear when we are in the active region. So where is the active region? So that's the important part. The active region. So this is another condition beside VBE that we have to take into account. So this condition we already know. So this is the cutoff condition or cutoff region that we found here. The cutoff condition is, of course, is when the voltage is around 0.6 or 0.7, which is the bias voltage. The next region is the what we call the saturation region. What is the saturation region? The saturation region is when our VCE is basically the saturation region. It's not the saturation. The active region. The active region, when we have VCE. So here VCE is larger than 0.2 or 0.3 volts. As VCE is larger than 0.2 or 0.3 volts, now we are in the linear region, which is called active region, right? So here is the cutoff region, here is the active region. And in this condition, what we have, VCB. Where is VCB? VCB is basically this voltage, VCB. The consequence of both of this is that in VCB, we will have VCB larger than 0.4 volts. A more precise definition of the output characteristic can be found in this slide. So the first one, saturation region, as I mentioned earlier, saturation region is the region at the bottom. So what happened in the transistor is basically the saturation region is when both junction are forward biased, right? Both junction, PN on one side and NP on the other side, are forward biased, and IC increase linearly with VCE. So that's the saturation region. So this part, right? So when it increase linearly, this is the saturation region. I'm sorry, just now I pointed this one. It is this one. The next one is cutoff region. So cutoff region is the region that is on the x-axis, on the VCE axis. Cutoff regions, what happened in the transistor? Well, basically what happened is that both junction PN and NP are reverse bias. Therefore, IB becomes very, very small, and essentially no current across IC flows, or very small current across IC flows, right? Even if we increase the VCE, increasing VCE doesn't help in increasing IC. So that's what we call a cutoff region. So the important and the useful part or useful region is basically the active region, the region that we have here. Active region is the region where basically the transistors now act as a linear amplifier. A linear amplifier means where the BE junction, what we have in the transistor is basically the BE junction is forward bias and the BC junction is reverse bias. So any IC, an increase of IC will drastically increase also. Any increase of IB will in consequence increase drastically IB, IC. Of course, with the gain, with the coefficient, the ratio of gain beta, right? So beta is IC divided by IB. So saturation and cutoff region is areas where the transistors can operate as switch. So here and here, what happened is our or transistor just act as switch, but it won't act as amplifier. But in active region, the transistors can now also act as an amplifier. Okay, so after having looked at all the characteristic of a BJT, right? So what we want to do now is to try to solve and analyze a circuit where we implement a transistor in it. So let's say the question is to compute the parameters of the circuit by assuming that the gain beta in CE. So in CE, as we've seen just now, CE means common emitters. Assume that the gain beta is equal to 100, right? So when it says compute the parameters, so what does it mean by parameters? Parameters mean calculate the voltages across the junction in the across the transistors. So usually when we ask for that, the voltage that we want to measure is the voltage across the junction C and E, this VCE, right? This VCE. So we want to measure this VCE, right? So this VCE. So where is VCE? VCE is basically, if I put an arrow to show the difference potential of VCE, is actually it's VC minus VE, right? So it's the voltage at this point minus the voltage at this point. So that's what we call VCE. In order to be able to measure VCE, what we need is to solve the other parameters before that, right? So we'll see in this exercise how do we do that. So before that, if we have a question that looks like this, what happens is sometimes it might be confusing, right? So the thing that we can do is to redraw it into a circuit that represents better the components around the transistors. For example, here there is a point where we have a potential difference at this point. Voltage at this point is at 12 volts. What does it mean to have a voltage measured at a point? It means basically is the voltage between this point and a mass. So between this point and a mass, the voltage is 12 volt. And if the voltage is applied across the at the point of the collector, usually we will call it as VCC. For the voltage that is applied here at the junction of the base, so here is the base C, here is the collector, here is the emitter. Voltage at point B, a branch that leading to point B, we call it as VBB. So it's just in terms of notation. And the voltage that is can be measured at the point of E. This voltage is if there is a voltage, we would call it as VEE, but there's no voltage over here applied, right? So that's why here when we transform it into this circuit, we can see that we have this voltage applied. So it is basically a power supply. So we have VBB at B, at C we have VCC, right? And then the parameters that we are interested in that are gonna help us, there's another parameter which is VBE, because if you remember the characteristic, there are 3 points in the characteristics that we want to apply. The first one is to know that if it is turned on, the transistor is turned on, then VBE will be equal to 0.7 volts. So we will check later if it is turned on or turned off. If it is turned on, then we will consider that VB equals to 0.7 volts. And another point is that if it is turned on, it means the transistor would have a gain. In CE, the gain is beta. And what is beta? Beta is basically the ratio between IC and IB. Beta is IC over IB. So where is IC? IC is here, the current that get into the collectors, and IB is the current that excite the base of the transistors. And then finally, the other thing that we learn in the characteristic as well is if we apply a KCL over here, we can see that in CE we have the current that comes out from the junction of the emitter equals to IB plus IC. So these 3 characteristics that we have learned previously is the one that we're going to be using to solve the exercise in order to find, for example, to find VCE. The question is, when we ask for parameters, is to find what is VC, what is VCE. So let's have a look. So here the question is over here now. The thing that we can do is the first thing that we need to do is basically to check whether our transistor is in on mode or in off mode. So to do so, basically we have first one is to check if our BJT is on. So to do so, we assume that the BJT is in cut-off mode. What does it mean to be in cut-off mode? When it is in cut-off mode, it means that we have no current at the base. Therefore, we will not have current at the emitter and the collector. What is the consequence of not having IB, IE, and IC? So to know the consequence, what we need to do is we need to look at the to do some calculation across the circuit. So there are two KVL that we can see where we can write equations. The first one is KVL around BE. So BE is basically from base to emitter. There is this one KVL, and then the second one is around CE. CE is basically between this point and this point, right? So if we look at BE, the KVL in BE, what is the KVL? We have KVL in BE is we have VBB, right? VBB, so the current IB goes into this direction, so we have, I would call this as VRB, because this resistance usually called as RB, the resistance at the base. And then what else do we have in this loop 1? We also have VBE, and then we would have VRE, because the resistance we would call it as RE, resistance across the emitter. So that's where we get, if we look into the equation, so VBB is this 4 volts. VRB, what is VRB? VRB is basically this 40 kilo ohm, RB, which is RB, multiplied by IB, right? That is just Ohm law, RB multiplied by IB, plus here VBE, and then plus VRE over here. So we complete the loop now, starting from the ground back to the ground. So VRE, what is VRE? Again, VRE is just RE multiplied by IE, by Ohm law. So RE is 1 kilo, 10 to the power 3. Here we can see RE. So that's our first KVL. In second KVL, let's verify. So we will have the 12 volts. If we go here, so we have 12 volts equals to, so we have VRC. So what is VRC? It's RC multiplied by IC. So RC is 1 kilo multiplied by IC. Plus then we have VCE. Plus VCE. And then plus, so this, what is this? 1 kilo times IE. 1 kilo times IE is basically VRE. So this is VRE. It's RE multiplied by IE, right? So we have these two KVL. This is the first KVL, this is the second KVL. So how would we use this? We're back to checking the BJT if it is on or off. We said just now if it is off, then IB equals to 0, IE equals to 0, and IC equals to 0. Let's plug in the value of IB, IE, and IC equals to 0 into the KVL1, BE KVL where we have the junction BE. So if we plug in, so the equation that we get from here, it is this equation. If we plug in, for example, IB equals to 0, IE equals to 0, then that would mean that at the end we will have 4 equals to, so 40 times 0, we have 0. Here is 0, 4 equals to VBE. So we found out that VBE equals to 4. And when VBE equals to 4, we know that 4 is larger than, it is basically larger than the bias voltage. If it is larger than the bias voltage, it means it is turned on. It is basically on and it is not off, right? It is not off. So that's how we verify whether it's turned on or turned off. Once we verify that, then it means we can take into consideration that VBE is, we can use the properties, the characteristic that VBE equals to 0.7 volts, and we'll have IB larger than 0, which we don't know what's the value yet, that we have to find later. So in next slide we'll see how do we find it. So just now in previous slide we have checked if basically the transistor is on or off. So we have concluded that the transistor is on. So what's the consequence of its being on? The consequence of being on is that all the characteristic that we have seen previously is applied. So the characteristic is, the first one is we know that VBE equals to 0.7. So we consider that we have a semiconductor of silicon. And then the question also says that we would have beta equals to 100. So what is beta? Beta is the gain coefficient, where we have IC equals to beta IB, right? So that's the second characteristic that we're going to use. And then the other characteristic that we can use as well is the KCL in the transistor, in the junction of transistor, which says that IE equals to IC plus IB. So let's look at this first. We know that IC equals to beta IB, so we can replace basically IC in here. It gives us an expression of IE that only depends on IB. So now IE becomes, so IC is beta IB, right? So IC is beta IB. We have beta IB plus IB. So we can simplify the writing of IE into just basically it's beta plus 1 multiplied by IB. Now we can get rid of IE, or if we have IE, we can write it in terms of IB. So let's look back at the KVL that we had. So the KVL, there was one in this loop and another one in this loop, right? So basically we also have a ground here, 12 volt here. We call this as VCC. We call this as VBB. Sorry. So the first KVL was VBB equals to, so VRB which is RB multiplied by IB, plus VBE, and then plus VRE which is RE multiplied by IE. So the first remark that you can see that is now knowing that we apply the characteristic that we've seen here, because we have the transistors on. Now we know the value of VBE, which is 0.7 volts. VBB, we know the value, it is 4 volts. RB, we also know the value, so RB is the resistance over here, it is 1 kilo. IB is the thing that we don't know yet, so it's a parameter that we want to look for. RE, so RE is this, RE is also 1 kilo ohm. And then IE is something that we don't know, right? It's also something that we don't know. So this equation has two unknowns, IE and IB. But if you look at here, IE can be written as a function of IB as well. So we can write VBB is also equals to RB IB plus VBE plus RE multiplied by, so we've deduced that previously IE is beta plus 1 IB. So now having this, we see that this equation, the only unknown is IB. IB, this is the only unknown. We know all other parameters, we know it. So from here what happened is we can calculate IB. So I'll let you do the rearrangement of the equation, but at the end what you will find is that you'll find that IB equals to 54 microamperes. So IB equals to 54 microamperes. If we have IB equals to 54 microamperes, it means that we can also calculate IC, which is equal to beta IB. So it's 100 times 54 microamperes. So now we have two things.
IB and IC. So knowing IB and IC, what we can know next is basically IE, right? So therefore we have IE, which is equals to IE is IB plus IC. So IB is 54 microamps, and then plus, so basically 54 multiplied by 100, we would have, I'll just write 5400 microamps. So I'm just going to leave it like this for a moment. So now we know all the parameters of IB, IC and IE. So what's the other thing that we don't know? The other thing that we would like to know is basically it's VCE. So where do we find VCE? It's in the second loop, in this one. So in second loop, we can write, what we can write is VCC. So VCC is this 12 volt equals to VRC. So this is VRC, voltage across RC. It's RC multiplied by IC plus VCE. So is the parameter that we're looking for, that we don't know. IC, now we have found it here, right? Or here to be exact. So RC known parameter, IC known parameter, plus VCE, and the other one is basically it's VRE. So VRE is this voltage. It's RE multiplied by IE, and again RA is a known parameter, it's 1 kilo ohm, and IE has been found here. So now VCC we also know is equals to 12 volt. Now we can deduce VCE easily, which is VCE equals to VCC minus RC IC minus RE IE. So I'll let you replace the value. So VCC is 12 volts, RC is 1 kilo ohm, IC is the value that I found previously, so it's 5400 microamps, RE is also 1 kilo, and IE is this value. IE is 54 microamps plus 5400 microamps. So if we do the calculation, then we'll find VCE. So that's all what you need to do. Find the parameters, mean find what's the value of IB, IC, IE and VCE, right? That's what we want. And the steps involved are all the steps that have been shown here. So it's not complicated, it's just to basically to apply all the knowledge, all the prior knowledge that you have previously, KVL, KCL, and then just applying the characteristic, the condition of utilization of a transistor. Alright. So now here we have another example. So it's example number 2. This might seem more complicated, but there's nothing complicated in here. It's the same thing. So you give a parameter of beta equals to 150, VBE equals to 0.7. So it assumes that the transistor is on, so you don't have to do the checking anymore. And it asks you to find V0. Where is V0? V0 is the voltage that's shown here. V0 is basically VCE, because this is the collector terminal, this is the emitter terminal, and this is the base terminal, right? So again, in order to do so, we have basically to calculate VCE, we need to write the KVL in this loop tree. And in this loop tree, we will be needing VRC. So this is, I will call this as RC, and we will be needing also VRE. So we need IE, and then we need IC. So again, we come back to the same conclusion. What we need to calculate is basically IC, IE, and in order to calculate IC and IE, we will use beta, and we will need before that IB. So the key to it is to start first with finding IB. What is IB? If you find IB, then you'll be able to find IC, because IC is just beta IB, and then you will also be able to find IE, because IE is just IC plus IB. So what is IB? And once you have find IC and IE, you can just replace it in VRC using Ohm law, in VRE using Ohm law, and you can write the KVL inside loop 3, and you'll find VCE. That's easy. So the one thing that we need to find is what IB. What is IB? So how would you tackle this? Now if we look into this structure, we can remark that there is basically a voltage divider. So again, it's a usage of prior knowledge that we've learned in previous chapter, right? So voltage divider. So where is the voltage divider? If I have to redraw, we have the supply voltage equals to A. So A should be, of course, should be given. And then we have, I will call this 100 kilo ohm as R1, but I'm drawing it now in a different in a different way, but it's still the same thing. So I have R1, and then after R1, basically I have a junction, right? And then here underneath I have R2, and here we have mass, right? And this is, I will call this as VR2, voltage across resistance 2, and here you have VR1, voltage across resistance 1. And then where is IB? IB is the current that goes out here. Here we have, I would call it as I1, it is called as I1. And then here we have I, is called as I2. So how do you find IB? To find IB, it's easy. If we look at this node, we can write a KCL at this node. I'll call the node as node star. So KCL in node star, on node star is, what is the KCL? So the sum of entering current equals to the sum of leaving current. So it's I1 equals to I2 plus IB. So it means if you can find I1 and I2, you'll be able to find IB. And if you can find IB, you can solve the whole exercise. So how do you find I1? So I1 is the current that goes across R1. I1 is, of course, if we write the Ohm law, if I call the voltage across R1 as R1, I1 is VR1 over R1, right? It's over here. It's VR1 over R1, and I2 is it is the same thing, but now it's VR2 over R2, right? It's VR2 over R2. So the question now is, what is VR2 and what is VR1? So now we will use the properties of voltage divider. VR2 is basically a portion of the voltage of A. If you want to calculate VR2, voltage divider say that VR2 is equals to A, the whole voltage, multiplies by the resistance R2 over the sum of resistance across the junction, which is R1 plus R2. So that's VR2. We found out VR2. That's easy. Next, what is VR1? If I can find VR1, that means that in this loop, if I write the KVL, I'll find that A minus VR1 minus VR2 equals to 0. That means I can find VR1 equals to A minus VR2. We found VR2 over here, and A is something, a value that's given, so I will know the value of VR2. Now, knowing the value of VR1 and VR2, I can therefore calculate I1 and I2. And then I'll find IB, which is I2 minus I1. Once you have found IB, go back here, we calculate IC, calculate IE, and then once you have IC, IE and IB, we can go calculate write the KVL in loop 3 and find VCE. So I'll let you finish this part, right? So that's basically what we do in transistors. Just use the same properties, and then just play around and try to figure out how to find IB, because this is basically the most important parameters. Is the current that actuate or switch on the transistor, and if you found IB, then the rest you will find it, right? So that's all about the exercise, and now we will look at another example of configuration of transistor that might be interesting to use. So the another configuration of transistor that is interesting to use is what we call the Darlington transistor, right? So what is Darlington transistor? Darlington transistor is basically just an arrangement of two standard transistor, either NPN or PNP, which are put one after the other. So why do we do this? We do this basically is to achieve two things. The first one is to get a more sensitive transistor and a larger current gain. So for example, if we have a typical value of beta of the gain, it's ranging from 50 to 200. If it is insufficient, then we might want to increase the beta. So how do we increase the beta? Is by putting basically two transistors in this configuration, one after the other. Of course, it will be the same type, NPN or PNP. So the method is to put the emitter current of the first transistor, TR1. So the emitter current of the first transistor, we make it we use it as the base current for the second transistor. So TR1 is connected basically TR1 is connected as an emitter follower and TR2 as a common emitter amplifier. And what is the new gain? The new gain is basically just the product of the two gain of the transistor. So imagine if you have the gain of the first transistor at 50 and the second is also at 50, then the new gain is 50 multiplied by 50. Now we have a larger gain at 200 and 250. So this is the Darlington transistor. So this is the configuration if using two NPN side by side. This is when we use PNP side by side. So it's the same thing. The new beta, which we call beta Darlington, is the product of the two beta, the first transistor and the second transistor, right? And the new VBE, if you consider the totality, the assembly of the Darlington transistor, the VBE, the total VBE will be equals to VBE1 plus VBE2, right? So if they are the same transistor, which it will be equivalent or closely equivalent to 2 VBE1. Well, it depends basically on the precision of the measurement on the transistor. If the beta are really equals, then this can be applied. So little words on the advantages and disadvantages of Darlington transistor. We by using it, the advantages are we will be able to obtain a very high current gain. Beta is 2 times the beta. We will have a very high input impedance for overall circuit. Darlington pairs are widely available in a single package. They are available in single package, which are already arranged in that manner, and they are convenient and easy circuit configuration to use. The problem is that you will have a slow switching speed. So switching speed is not something that we have discussed here. Switching speed is basically if IB is not just one shot switching on. Basically, usually for example in an inverter, it use the input is basically coming from a pulse width modulation signal. If the frequency of that PWM is very high, then there might be a problem because basically each transistor has a switching time, which we call slew rate. And well, this is not discussed here, but there is something that is very important if we want to go further in the study of power electronics. And then we have, therefore, if the switching speed is low, then we have a limited bandwidth, and it can also introduce a phase shift. Phase shift means it introduce a lag between the input and output that can give problems at certain frequencies. The another disadvantage is to have higher overall base emitter voltage, which previously was 0.7, but now we will need more than 0.7 to turn it on. And then finally we will have also high saturation voltages, which can lead to high levels of power dissipation in some applications. I mean, we will create a lot more losses. So there are of course other type of usage and configuration of transistors. There are also other type of transistors other than BJT. There are FET transistors, but just for a chapter of introduction in this electrical and electronic technology course, this is what I think the most important thing that we need to look at, that introduce you to the basic of a transistor. Of course, for further knowledge, you can always look into more references on other types of transistors and other configuration of BJT as well. So that's all for transistor, and see you in the next chapter.